Okay, so here we have section 4.1, exponential functions. So exponential functions is another kind of functions that we're going to go over in this lesson. We're going to look at the different characteristics of the graph of an exponential function, and we're also going to learn how does the form of an exponential function looks like, which is what you see right here in green on the screen that I already have written down. The function may be written as f of x equals b to the x raised to the x power, or x equals y b to the x. You know that f of x and y is just a different way of writing the same thing. Specifically, b has to be a number greater than 0, and b can never be equal to 1. Okay, so b can be any number greater than 0, but b can never be 1. X on the exponent will be any real number from the ones that we know, right? Like any positive, any negative number, any integer, any fraction. It could be a decimal at times. It could even be, basically that any number that you can think of on the number line, it's a real number. So just learn from here that this is the format of an exponential function. Okay, this right here that I'm putting in red boxes. So let's learn a little bit more about exponential functions. Okay, one thing prior to learning, because we're going to learn in this section how to graph an exponential function, before we get to that part, we're going to go over how to use a little bit the calculator with exponents, which we've done already in the past, but we're just going to make sure that we know how to type things correctly when it comes to dealing with exponents. So, for example, 7 raised to the negative 1.4. In the instruction it says approximate the following number using a calculator. So all you're going to do is put 7 raised to that number. Now, you may type it exactly the way that I am putting it, 7, use the symbol for the exponent, and then the negative 1.4, or you may use 7 raised to, and if you want to, you can put a parenthesis here. At this point, it does not make a difference. The answer would be the same thing, right? When there are multiple exponents, then you do want to put a parenthesis. Here it's just one, so it doesn't really make a difference. Now, the instruction says to approximate to what decimal place or how many decimal places. It doesn't really say. You would have to read on the online homework, and it usually says round to 1 decimal place or whatever. So let's say that here we're going to round to 2 decimal places. Okay, so I'm going to put my symbol for approximation, and I'm going to round to 0.07, because after the 6 there's a number that is 5 or bigger than 5, and if that is the case, then the 6 changes to the next digit up. You round up. So 0.07 would be my solution, okay? But you can see here, and actually I'm going to take a screenshot of this so that you can have that here when this is light. Okay. So I chose to round 2 decimal places, I'm sorry, just because I wanted to read the instructions on the online homework. Okay. So what we're doing is really evaluating an expression that uses a decimal. That's all. Now here, something new that we can learn. How can we use the calculator to type something like this? What's E first of all? E, it's a number. If you put in your calculator just the letter E, and let me see on my calculator where the E by itself without, there's an E here if you see on top of where it says ln in this bottom, on the left side. There's also an E to the x power, but if you click on that one, I believe that it's going to open a space for typing an exponent. I do not want an exponent, so I'm pretty sure that there is somewhere here an E without an exponent. Don't see it right now. I think it's this one. Yeah. Second, and then the division symbol, it puts an E by itself. Okay. Sometimes later you're going to need to use an E without raising it to any exponent. So if that is the case, let me do it again. Second, and then division symbol. You can see the little E. You can barely see it here. Or if you need an exponent, second, ln, it puts already an e raised to some exponent that you're going to type. So that's the one that we need, second, and ln right here. So e raised to 2.3, it's 9 point, if we round this time, let's go again to 2 decimal places, so 9.97, because after the 7 there's a 4, so the 7 stays the way that it is. If the number is 4 or less, it stays. So approximation here, 9.97. And let me take a screenshot of that also. Oh, well, yeah, let me do a screenshot. I just wanted to tell you that if you're like, in what's e? E in reality is a number. Okay. It's just, I don't know if probably you've heard before of the number pi, right? Pi here in the calculator, for example, and we know pi equals to a number, a value. Second, and then the symbol for pi is right here. When you click on enter, the calculator already knows that pi has a value of 3.1415. You can see a bunch of decimals there. This number pi, it's a special number. It's a number that has a lot of decimals that are never ending, but at the same time, the decimals are never repeating a certain pattern. Okay? So something similar happens with e by itself. Second, and then the division symbol, and then you enter. That's the value of e. If you want to know what's e, e is a special number just like pi, where it has a bunch of decimals that are never ending. So the calculator already has stored the value of e. So when you put it, e raised to the 2.3, the calculator already knows that e has that particular value. If you don't have a graphing calculator, if you have a scientific calculators also have this number e, or the pi, or I mean, it has this kind of symbology, this kind of numbers also. But just to let you know, so you know now that e by itself, this is the value of it. Not that you need to memorize it, but I mean, I'm just letting you know. E here, it's not a variable. It's not like an x or an a. It's actually a number. Okay. So, moving on to the next slide. Characteristics of exponential functions of the form, okay, f of x equals b to the x. So this is the form of writing an equation that is an exponential equation or exponential function. Now there are several characteristics about an exponential function, specifically talking about the graph. The two curves that you see down here, the blue one and the red one, those represent the graph of an exponential function, each one of them, right, separately. We're going to see right now why one looks like the blue one from left to right looks like it's rising, going up, and the red one from left to right, if you observe it in that direction, it looks like it's falling, it's going down that curve, it's decreasing. So the blue one, we can say that it's increasing from left to right, and the red one is decreasing from left to right, it's going down. So we'll see how the equation of an exponential function would need to be for it to create either of these two shapes. So going here down on this list of things that you must know. The domain of an exponential function, okay, consists of all real numbers. So the domain, that's something that you have to memorize. The domain of an exponential function is all real numbers. The range of an exponential function is from 0 to infinity. Now, we are talking about the domain and the range of an exponential function that is called the parent function, like it's the basic function, right? So, every time that you have transformations of this basic function, you will still have exponential functions, but a transformation of the original, we already saw a section on transformations, you know that the range and the domain changes, right, according to your new graph. But if you want to make sense why the domain is this and the range is whatever it says here, let's look, for example, let's take, for example, the blue line. Look at the blue, not the blue line, I'm sorry, the blue curve. Look at the blue curve and look at it from left to right. So from left to right, think of the domain, so sideways, right? It starts somewhere on the negative infinity as you move your sight to the right or in that direction, this curve looks like it's going up, but at the same time you can see how it's kind of getting wider towards the right side. So that's why it's going to infinity. That's why the domain is that. Now the range, look at the blue curve starting from the bottom to the top. It looks like the curve is starting somewhere at 0. It's not touching the x-axis. It's, as a matter of fact, not going to cross over the x-axis. This relates back to something that we learned about asymptotes, but I'm going to get there right now. The thing is that this blue curve, or even the other one, they're never going to touch the x-axis. They're never going to cross over. Not in the originals, right? In the transformations, I mean, different things may happen. But the range here, it's 0 because it starts something at 0, like this curve starts at 0, and then it rises, it goes up, okay, to positive infinity. Same thing with the red curve. The red curve from left to right starts somewhere on the negative infinity. As you move to the right, goes to somewhere on the positive infinity, because these curves are going to continue, right? And the range starts at 0 and goes up to infinity. So the range and domain is the same thing for both. Now, number 2 says, the graphs of all exponential functions in the form, obviously, of this, of an exponential, pass through the following point. So all exponential functions pass through the point 0, 1. Okay? Why is that? Because this is the b is going to be a number every time, right? Let's pretend that it's going to be a 2, a 3, a 4, whatever. 4 raised to, let's say, 0, whenever this x gets to be 0, anything raised to the 0 power is 1. That's something that we have to memorize. Anything raised to the 0 power is 1. So that's why this graph, just memorize. Every time you have an exponential function, the function is going to pass through the point 0, 1. Obviously, again, if it is not a transformation, if it is just a basic exponential function, transformations, different story. So, since the graphs of exponential functions in this form are going to pass through 0, 1, you can see that point right here, okay? That also becomes the y-intercept. So the y-intercept is 1. There is no x-intercept. That's another fact that you have to memorize. There is no x-intercept in the exponential function. So as I was saying, there is no x-intercept. Sorry, I had to pause a little bit the recording. There is no x-intercept. Why? Because I'm telling you that by definition, these kind of functions are never going to touch or cross the x-axis. Either on top of the x-axis, they're not going to touch the x-axis, they're not going to cross the x-axis. They're just going to get really close to it, but they're never going to actually reach it. So this is, again, for the basic exponential functions, not for when we do transformations. Those may cross the x-axis, okay? Depends how the graph looks like. But if it is a basic, just a simple number raised to something, then to another value, for example, then it probably is going to look like this graph. So why is it that the graph cannot cross the x-axis, okay? And therefore there is no x-intercept. Because you can see here on the picture that it says that it looks like a dashed line on top of the x-axis overlapping it. There is a horizontal asymptote of y equals 0 right there. Okay, we already talked about horizontal asymptotes in the previous lesson, so you have a better idea of what that is. It's like an invisible wall that is there and is not letting the graph get close to it enough to touch it or to cross over it. Number 3 says, if b is a number greater than 1, so this right here, then the function is going to look like a graph that goes up to the right and is an increasing function. We can see that here, if b is greater than 1, okay, then it's going to look like the blue curve. In other words, from left to right, it's an increasing function. It goes up. Okay. The greater the value of b, the steeper the increase, okay? Now, if b is a number that is between 0 and 1, then the graph is going to be like the red graph that you see here, the red curve. So that function has a graph that goes down to the right and is a decreasing function. The smaller the value of b, the steeper the decrease will be. Number 5 says, this is just a fact, but I mean really you don't really need to know this, but it says that we already learned in a previous section what a one-to-one function is. It says that any exponential function, it's a one-to-one function all the time, and it has an inverse function. Any exponential function will have an inverse. We'll talk about those later. Number 6 says, the graph of this exponential function approaches but does not touch the x-axis. The x-axis or y equals 0 line is a horizontal asymptote, which is this right here, okay, the dash line that you see there. So these are just general concepts that we might not need to memorize at this point, but it's good to know, okay? So moving on to the next slide, and the first actual problem where we have to do something dealing with an exponential function. We have to graph this function. Okay. So to graph it, I know that we can use the calculator, as I always say, that we can get points from the calculator. In this particular section, we do want to spend some time thinking how can we deal with exponents to create this graph. Okay. So for example, when I graph this 5 to the x, let's look how this looks like on the calculator. 5 raised to the x looks like this kind of curve. Okay. So you can choose whatever x's you want to choose. You can go here if you want and choose any x's that you want. The thing is that we want to learn how to deal with exponents when they're positive or when they're negative. And see, here in this function you're going to be substituting into the x. So I say, I don't know, let's choose a couple of negatives, the 0, and a couple of positive x's. So maybe choose -2, -1, 0, 1, and 2. We might need to choose more, we might not. We'll see right now, depending if these points give us a good idea of how the graph is going to look like. Maybe that's good enough. So I'm going to be doing here the substitutions. F of -2 means 5 raised to the -2. Okay. So how are we going to deal when we have by hand, right? Because I know you can put this in the calculator and it may give you the answer. But how do we do, because you need to know for other sections how to do this by hand. How can I do 5 raised to the -2? Well, you simply put your 5 over 1, you flip it around, so you have 1 over 5 raised to the 2nd power. If you simplify this, this is 1 over 25. So right here, this is 1 over 25. And if you're going to be, and how am I going to plot that? What is 1 over 25? Well, that's one where you could actually use the calculator to change that number into decimal. It would be 0.04. If I go to my table, let's look for -2. Look at the y value, which is right there. Okay, but we need to know how to deal with the negative exponent. So f of -1, I'm going to need to go lower because I don't have space. 5 raised to the -1. Okay, so you already know what you need to do. Create a fraction. That's why you put it over 1. Flip around the number. But when you flip around the number, the exponent becomes positive. So now you have 1 over 5 to the 1st power, which that would be the same thing as just simply 1 over 5. Okay. So what would be 1 over 5 in the calculator? 1 divided by 5, 0.2. You go to the table. Let's look at -1. The y coordinate is 0.2, 0.2. Okay. F of 0. 5 to the 0 power. This is a definition. Anything that you raise to the 0 power, it could be a number, it could be a variable. The answer will always be 1. If you put it on the calculator, 5 to the 0 is 1. That's a definition. You must memorize that. Okay. And then f of 1, 5 raised to the first power, that's a simple one, just 5. And f of 2, 5 to the second power, 25. The only times that I'm putting a 1 under the integer, under the number, and flipping it around, if you see, is when I have a negative exponent. And you do that to create a positive exponent, because when that fraction flips, the exponent becomes positive. So now it's just a matter of plotting this point here. Okay. We said 1 over 25 was 0.04. So I'm going to plot negative 2, 0.4, 0.04, I'm sorry, 0.04, somewhere, let's say here, we're estimating. 1 over 5 was 0.2, so negative 1.2 is slightly above that one. It has to be somewhere above. 0, 1, you see how we said that every graph of every exponential function has to pass through this point 0, 1. You can see it here. And that's the y-intercept. It's going to cross the y-axis right there. 1, 5, and 225. Now, 225 might not fit, right? So I'm not going to put that one. But you'll see that it would be a point in a higher value on the one, that it's not even going to fit in here in my graph. And I really don't want you to think that this is going to be like a super sharp graph, like where it's going to go as a straight line here. That's why I went, let me do this again. Okay, so something like that. I know it's the same, but I want you to understand that even though that the way that I did the graph, it looks like my curve over here, it's touching on the bottom part, the x-axis, on the calculator, it gives that impression too, as if it was actually touching the x-axis or overlapping it. It's really never gonna touch it or cross it. It's just, I mean, it's impossible for us to draw it and not make it seem like that. But you know the definition. In reality, there is here a horizontal asymptote. Okay, a horizontal asymptote at y equals 0. We see that from the graph. I see the graph never crossing below here. There's no piece of this graph under the x-axis. That means that there is something here preventing the graph from crossing over. That's how I know that there is a horizontal asymptote. And because I also know the definition of exponential functions. They have an asymptote that is horizontal. Okay? An invisible horizontal line. So this is how you do the graph of an exponential. Now, can you just copy numbers straight from the calculator and put them here? Yes. But I'm telling you, later, if you do not know how to deal with negative exponents by hand without the calculator, you're going to regret just doing it only on the calculator. So learn how to do it by hand and verify with your calculator. It's okay. So in the next slide, we're going to graph another exponential function a little different. This one, and it's g of x. What's the difference between this one and the other one? I mean, the way that you're going to graph it should not change. What happens on this one is that instead of b being a number greater than 1, and I'm going to go back a little bit. Remember that when it says on this graph that whenever b is greater than 1, it's going to look like the blue curve in that direction, rising from left to right, or increasing. Well, this one looks like more or less like that shape. This one, 9/2, 9/2, in decimals is 4.5. That's still a number greater than 1. So the shape should be the same as this one. I mean, not exactly having the same points, but the shape overall from left to right needs to be rising. Okay. So let's choose a couple of numbers to substitute. Uy. So just to give ourselves an idea, let's put this on the calculator. Just the way you see it, in parentheses, 9 divided by 2 raised to the x power. We graph it. You can see how it follows the same shape. So can we choose the same values? Yes, why not? We can choose -2, -1, 0, 1, and 2. Let's do the same drill again. F of -2 equals 9/2 raised to the -2. So how do you deal with having a whole fraction raised to a negative exponent? Not the same as just having a single number, a single integer raised to a negative exponent. When you have a single integer, we put it over 1, we flip it around, and the sign changes of the exponent. Here, what you have to do is you already have a fraction, so you don't have to do that step of over 1 to create a fraction that you didn't have. Now you do have it. So all you do is flip around this fraction the way that it is and make your exponent to be positive. Okay? Now raise these two numbers each to the second power. 2 to the second power means 2 times 2, 4. 9 to the second power means 9 times 9, 36. Okay. Now ask yourself, can I reduce this number? Yes, both numbers can be divided by 4. So we have 1/9. So that's the value that you're going to put here. Again, you know that you can change 1/9 in the calculator to decimal. So 1 divided by 9.1. Okay. Now, what's f of -1? Again, 9/2 raised to the -1 equals 2/9 raised to the first power. Once you flip around the numerator and denominator on the fraction within the fraction, then the exponent becomes positive. So what's 2 raised to the first power? 2. What's 9 raised to the first power? 9. Same thing. 2 9. F of 0 is going to be 9/2 raised to the 0 power, which is 1. Then we have f of 1 equals 9/2 to the first power, again. So 9 raised to the first power is 9, 2 raised to the first power is 2. Probably didn't made enough emphasis, but anything raised to 0, the answer is 1. And here you may be saying, but there's two different things. Okay, so everything that's inside is raised to the 0 power, right? So then everything becomes a 1. Okay, just like when you have a whole integer raised to a 0, I mean, it's the same thing. You can even do by parts. 9 to the 0 is a 1, 2 raised to the 0 is 1. So what's 1 divided by 1? 1, same thing. So that's what goes here, 9/2. And then the last one, it's going to be f of 2. 9/2 raised to the second power. 9 times 9, it's going to be 81. And 2 times 2 is 4. And I don't think this is a reducible fraction. I mean, 81, thinking of the times tables, is divisible by 9. I don't think it can be divided by anything else. Okay. So it was just the first one that we were able to reduce. So now let's plot the points that we got, okay, from this table. Obviously, there's a bunch of decimals that you're going to have to change into, a bunch of fractions that you're going to have to change into decimals. So 1/9, it's 0.1. So -2 with 0.1 right there. 2/9, or 2 divided by 9, it's 0.222. So -1, and slightly above that one, 0/1, 9/2, it's going to be 4.5. So 1 and 4.5 right here. Okay, I'm assuming this is 5, so right here. You can see in the previous dot that we put, the previous point, 0, 1, again the same y-intercept that by definition was saying that every exponential is going to pass through that point. You can confirm that again. And then 81 divided by 4 is 20.25. It's not going to fit anymore, that last one. So we're just going to not use that one. Do the graph again. Okay. So more or less that you have your graph. Let me just redo this point. And that's it. Again, where is the horizontal asymptote? Right here. Okay, there is a horizontal asymptote of y equals 0. Okay. So that's what this is. Okay. Now next problem, use transformations of the graph of f of x equals 2 to the x to graph the function h of x given below. Graph and give the equation of the asymptote. Use the graph to determine the domain and range of h of x. Okay. So we need to do a table of values. If you recall, we used to graph first the original graph. What's my original? This one right here. Okay, 2 to the x. Using that one, we're gonna graph this transformation right now in the next tables. So here we're gonna graph within the same coordinate plane both. It says use the graph to determine the domain and the range of h of x. Determine the domain and the range of h of x. We have to graph and give the equation of the asymptote of h of x. Equation of the asymptote again of this one, the transformated. Same thing here. Graph the function and its asymptote. Graph the asymptote as a dashed line. Use the graphing tool to graph the function. So if we really want to go step by step using transformations, let's use 2 to the x, and let's copy just to make it faster. You already know how to substitute values for the x and work it out with 2 to the x, but just to make it easier for ourselves, let's copy some points from here. I'm just gonna do -1 with 0.5, 0, 1, and 1, 2. I'm gonna do less points this time because this means more work. So -1, 0.5, 0, 1, 1, 2. Okay, so here we're gonna have our first exponential function. Okay. And let me redo the points. It was 1 was right here, 0, 1, and 1, 2. So now doing transformations, okay? I'm gonna go step by step. I'm gonna do, the first thing that I'm going to do is doing this, moving the graph to the right side. This +1, it's like when we went over transformations and we learned that whenever inside of a parenthesis, inside of a square root, we have something that is being adding or subtracting, we're gonna move sideways and we're gonna move in opposite direction from the sign that we can see in that particular expression. So in this x +1, we're gonna move every point from this graph 1 unit to the left. Because of this +1, it means 1 unit to the left. So that means subtracting 1 to the x's basically. So negative 1 minus 1 would be a negative 2, 0 minus 1, negative 1, and 1 minus 1, 0. The y's right now remain as they were before. Okay. The next table, it's not going to fit here, so I'm going to do it right here, below this one. So now what we're going to do, and I'm going to write again this transformated function, equation I was going to say, but function. This means 6 units up, so, or upward. So that means that now the x's stay the same, but to the y's we're going to be adding 6. So 0.5 plus 6, 6.5, 1 plus 6, 7, 2 plus 6, 8. So now the new graph would be, let me use another color, negative 2, 6.5. So negative 2, 6.5 would be more or less right there. Negative 1, 7. So negative 1, 7. And 0, 8. Right here. You may say, that is going to look like a line. Well, remember that our functions in this section are exponential functions. Exponential functions do not look like lines. Let's grab the transformated one and see how that will look. Now, you need to be careful. You need to use a parenthesis around the exponent of the 2. The whole exponent is x plus 1. So you need to put a parenthesis around that because there's multiple things adding or subtracting on the exponent. Then plus 6. So the plus 6, do not put it inside of the parenthesis anymore. You graph it, and you can see the curve really high up here. So I'm going to connect all dots, trying to do the same shape as what I see on the calculator. Okay. So you see, once you grab the transformated function, this does not pass anymore through the 0.01, right? I mean, because it's a transformation. So it's a variation of the original or the simple exponential function. So now, the question here is that they want me to find or identify what the, and I'm going to use another color, the horizontal asymptote would be for this one. Well, it looks here, if you would count the units, it looks like it's approaching 6, but it's never going to touch the 6. So that would be your horizontal asymptote right here for this one, for the transformation, right? I'm just talking about the transformation. So the horizontal asymptote here would be y equals positive 6. Now, you may be thinking right now, oh, so I know what usually the horizontal asymptote is going to be. The number that is being adding or subtracting to the function, but that is like to the side. The number that is usually a vertical translation, a vertical shifting up or down, that is usually going to be your horizontal asymptote, and you are right. Every time whatever number here represents a vertical translation, a shifting up or a shifting down, so many units, that's exactly the number or the value through which you're going to have the horizontal asymptote for the transformated version of this original function 2 to the x. For this one, the horizontal asymptote would be as the original basic exponential function. The horizontal asymptote would be at y equals 0. Okay. So this pretty much falls into something that we already know, transformation. It's just doing transformations with a new kind of function. Okay. So you can see that we can even apply transformations here. Okay. So you can take an overall look at the whole thing. Okay. This problem, same thing. You need to do a transformation of the original function. What's the original here? 4 to the x. What's the transformated equation or function of that? 4 to the negative x. So, okay, f of x equals 4 to the x. We do a table of values. If I want to see how this looks like on my calculator, it's going to be, 4 raised to the x power. Okay, still going to look like the same shape. I'm going to try to go faster this time. So negative 1, 0.25. Why I'm choosing negative 1 to start? Just because. 0, 1, like no particular reason. And 1, 4. Okay. So first transformation, well actually there's only one transformation here. Okay, there's not anything else to do. So we're gonna do, okay, what is going to happen when we have a negative? If you recall back, what happens when we have a negative in front of an x, not in front of the whole function, right? But in front of just a single x, that means a reflection over the y-axis. That means that you're going to multiply the x values times negative 1. So negative 1 times the negative 1, positive 1. 0 times the negative 1 is still 0, and 1 times the negative 1, negative 1. The y stay the same. You can go back to the section where we learn about transformations, and you'll see that's what the definition is of when you have a negative sign in front of a single x. Okay. It's just we're using a different function, but it's the same thing. So plotting the points 1, 0.25, so let's say somewhere here, 0, 1, and negative 1, 4. Okay. So I had already graphed here 4 to the negative x. So 4 to the negative x, when you graph it, looks like this. Okay, our points kind of make sense, that when we connect them, it's going to look like that. So all you need to do is do the graph, more or less, right? Okay. So now, what would be our horizontal asymptote? Well, the same thing. Horizontal asymptote would be located at y equals 0. How do we know that? Well, we can see that the graph, like it looks like it's touching or overlapping the x-axis, but we know it's not going to. Remember that I said the number that is the transformation that moves or shifts the graph up and down, that would be your horizontal asymptote. Like the previous problem, the 6, the plus 6, that's what the horizontal asymptote was for the transformation, the transformated exponential function. So why is it that when we don't have that plus something, minus something to the side, the horizontal asymptote is always at 0? Well, because there is actually, like, technically, like if you would have here a plus 0 next to the negative, next to the 4 raised to the negative x, if you want to see it like that. Okay, it's like if there is a plus 0 right here. Okay, and that's why the horizontal asymptote is just 0. But you know, writing plus 0 doesn't make sense. I mean, we don't need to. But that's basically why. Okay. So this one was a simple one. Transformations of equations or functions that deal with e to the x. Okay. So the original function is e to the x. Let's graph that in the calculator and see how it looks like. Second ln, where you have the e raised to the x. So you can see how that would be. You copy some points from the table, which numbers, whichever you want. So -1, and I'm going to estimate -1 with 0.4, 0, 1, and 1 with 2.7. The graph has to look like that. So -1.4, more or less right there, 0, 1, 1, 2.7. So let's say right there. Connect them. And you can see my graph right there. Even when you're doing your graphs, I know that it's impossible not to make the graph look like it's not touching like the x-axis, but it's okay. If it touches it, I mean, at least just show the horizontal asymptote that you know that goes here, right? At y equals 0. Because it's almost impossible not to make it touch there. So the transformation, the only transformation that I see here is multiplication of the original function times 2. So what is that going to change in my table? It's going to change my y values. So the x's, the x's are going to remain the same. The y values are the ones that are going to be multiplied times 2. So when you have a number multiplying times a whole function, this means that you're going to multiply y values times the indicated value. And it's going to cause your graph to look like it is enlarged, like if it is vertically stretched. So I'm going to put here vertical stretch. So when I multiply this y times 2, 0.4 times 2 is going to be 0.8. 1 times 2 is going to be 2. 2.7 times 2, it's going to be 2.7 times 2, 5.4. So plotting this point, -1, 0.8, so a little bit above 0.4, right here. I should probably use, what color can I use? I've been using them all. I'm going to try, hopefully you can see them. So there, I know that it looks like if it was already touching here, but I mean, it's, what else can I do, right? Like, you get the point. It's a little bit lower than 1. So -1, 0.8, 0, 2, 1, and 5.4. So 5.4, we're going to say that it's more or less right there. So when we do our graph, I should probably make it in black. Our graph is going to pass through this point in the following way, forming this curve. That it almost seems to be the same thing as the other one, but due to that multiplication times 2 of all the y's, it's a little bit higher. That's all it is. So what would be the horizontal asymptote for this one? It would be, so for this one it would be still be 0 the horizontal asymptote, y equals 0. Why? Because I didn't really do a good job here, but technically this is gonna keep going down to the point that it looks like it's gonna reach this other one or touch this other one. Why? Remember that the horizontal asymptote is whatever value that is being added or subtracted that causes a vertical stretch. Well, here I don't have a plus something, a minus something to the side of 2 times e to the x. There's not a plus something, minus something. So then it's like if there's a plus 0, so the horizontal asymptote is still the same. That didn't change. All that it happened is that the graph got enlarged. And probably you don't see that very well here. But look, if let me put e to the x, that's the original, 2 e to the x, that's the original, and that's the other one. So looks like we lifted up a little bit. You may think it's shifting up, but it's not really that. It's like if it was pulled from the upper side of the coordinate plane, or it was vertically stretched, okay, in a vertical way. So that's what it is. Okay. Now this last part on this lesson. Now we're going to stay away a little bit from the graphing part. We have to use or learn about some formulas. These formulas are called compound interest formulas. There's 2 formulas basically, okay? There's for compounded period per year, and so you're going to be using this one. Or you have the formulas for continuous compounding, which this is the formula. Now, what's the difference? How to know when to use one or the other one? Let me tell you the key. When the word problem says continuous, okay, the word continuous is going to say compounding, but it's going to say continuous. This is the formula that you're going to use. If it just says compounding, but never the word continuous is mentioned, just compounding, then this is the formula that you want to use. Okay, this right here. So it's good to know what each of these variables mean, because you're going to be like, and what? This is used for problems dealing with money. This formula, you may say, and what does this have to do with what we were seeing right now? Graphing. Well, you were graphing exponential functions. These equations or these formulas are exponential formulas because they have exponents. So it's an application, an extension of just simply doing the graphs of some equations that have no meaning whatsoever. Here is an application. That's what this is. So A here represents future value. P represents present value. Usually the present value is an invested amount or an investment. It's something that you're going to invest, or someone is investing into an account, or something like that. Okay. The R in both formulas, it's the rate. And I'm going to tell you something. The rate is always going to be given to you as percent form. You always have to divide by 100. Divide by 100 before using the actual rate number into the formula. N means how often in a year or within a year. Now you see the second formula, continuous compounding, does not have an N. So this N just applies for the first formula. And here A, P, and R have the same meaning in both formulas, okay? So now when I say how often in a year, it's because we are talking, well, I can probably put it here and just keep it this way. We are talking that it could be annually. That means one time in a year. It could be daily. That means 365 days in a year. So every day of the year. It could be quarterly. So 4 times within a year. It could be monthly. So you have to think, how many months are there in a year? 12. So every month, some interest that will be accumulated. Let me think if there's annually, it's 1 time in the year. Daily is 365 days. Quarterly means 4. Monthly means 12. And I think that should be it. I don't think those are the most common vocabulary words that I see that they use in this problem. Okay. So let's go to the application. So remember, how to know when you're going to use one or the other formula with whatever word problem they're going to give you, because these are going to be reading problems. If it says compounding, is the first one. Continuous compounding, continuous, that's the key for using the second equation. The E here, what is the E? It's a number. You already know that it's a number in the calculator. So moving on here, use the compound interest formula. A equals P times 1 plus R over N raised to the N times T. These two N's are the same N, okay, by the way. So whatever value you put in one N, you also put it on the other one. So use the compound interest formulas, this one and this one, also the other one, to solve the problem given. Round the answers to the nearest N. Find the accumulated value of an investment. Let's underline the things that we see that are important. So the investment. Find accumulated value. So this is the question. You're going to find accumulated value of an investment of $10,000 for 7 years. This would be your time. Oh, and I forgot here on the previous slide, the T, it's because it almost doesn't look like, or it doesn't show like it is a T, but T represents time elapsed. Okay. So we were saying here, find the accumulated value of an investment of $10,000 for 7 years at an interest rate. Here is your rate of 4%. If the money is A, compounded semi-annually, B, compounded quarterly, C, compounded monthly, D, compounded continuously. This is the one that I was missing. Semi-annually means 2 times within a year. Let me go back to the notes and also add that one there. So I'm going to put here semi-annually, 2 times within a year, every half of a year. So okay, let's do piece by piece. A, compounded semi-annually. So it doesn't say the word continuous. That is my hint to know that I'm going to use the formula that looks like it's longer than the other one. When it doesn't say continuous, when it does not say the word continuously, just compounded semi-annually, compounded quarterly, whatever, it's this long formula. You need to know what's what. Okay. Find the accumulated value. It's money that accumulates over time. So you're finding future value. Your A is what you do not know. So that's going to stay the way that it is. P is the investment. Remember that I told you P is the present amount or the investment? So you put 10,000 times 1 plus what's the rate? 4%. But remember what I told you. Divide 4 by 100 all the time before you use it in the formula. So you're going to use 0.04 or 0.04. The thing is, the percent needs to be divided by 100, and that gave me that, and that's how I used it here. The N means how often within a year. Semi-annually, I told you it's 2 times within a year. And on top, in the exponent, you have N times T. N is 2, I'm going to put in parentheses, times the time. which is 7 years. And all you do is work this out. Now, you can work it out piece by piece, or you can put it all in the calculator. It's really up to you. If I work piece by piece, what would be the first thing that I'm going to have to do? The inside of the parentheses. Simplify all this thing inside. 1 plus, in parentheses, put 0.04 divided by 2. The fraction, put it in its own parentheses. So all this, it's 1.042 raised to that. 2 times 7, you can already do that, 14. So you have 10,000. That is multiplying times this number raised to 14. So before you say, let me multiply 10,000 times this number, you can't, because the 1.042 has an exponent. It's been raised to an exponent. So 1.042 raised to 14. That's 1. Let's round to 1 decimal place, to 1.8. So now you can multiply 10,000 times 1.8, 18,000. So this is money, right? We were talking about money. So over a period of 7 years, someone is investing $10,000 at a rate of 4%. So that means, and it says semi-annually, compounded semi-annually. So every half of a year, this person is going to add to that 10,000 that he or she is investing 4% of that amount. Okay. So after 7 years, this is how much it has been accumulated. So the amount obviously grew, grew. It's more now. So I did everything step by step. Now, do you want to do everything at once? You can, but you need to be careful how you enter things. 10,000 times 1 plus, remember that I told you, parentheses for the fraction, 0.04 or 0.04 divided by 2. Close the parentheses for the fraction. Then close it again for the parentheses that you're supposed to put for all this. Raised to that. Since the parentheses here, I put a parenthesis on the exponent. Make sure you also put that parenthesis, 2 times 7, because there's multiple things on the exponent. If you don't type it the way that I am typing it, you're going to get, oh, why did I get something else? It could have been because of the rounding, because this number here that I rounded in the parentheses, it's so different from what it's supposed to be. But I don't know, it's too much of a difference. Okay, I think I figured what I did. I typed something wrong on the calculator, I think. Or I copied some, I don't know. I went back to, okay, maybe I did a mistake when I did this inside of the parentheses. And yes, 1 plus 0.04 divided by 2, I think I added an extra 0, or I ate a 0, I don't know what I did. This is 1.02, not 1.042. 1.02, you can see that here. So when you raise that number to the 14th power, this is not 1.8. If we round to 1 decimal place again, it's 1.3. So yeah, it makes more sense now. When I do 10,000 times 1.3, that's 13,000. Okay. So the answer, when I plugged everything in here, you don't see it anymore. So let me type it again. 10,000 times 1 plus 0.04, and I wasn't going to put the parentheses. 0.04 in parentheses divided by 2. Close the parentheses, close the other parentheses, raised to 2 times 7. If you put everything that you had since the very beginning, this is the answer now. why is there a difference of $194 and some cents? Because I was rounding this number right here. When I did 1.02 to the 14th power, I cut a bunch of decimals. Look what it was supposed to be. 1.02 to the 14 in the upper part of the calculator is 1.31, like a bunch of decimals. Since I'm rounding, but I'm chopping in reality a bunch of decimals, the answer has to be different at the end. So what would because you know it's very, very picky, the computer, when you're doing the online homework. On paper, on test, I wouldn't mind. If you do like me, like Hannah, you get 13,000, it's fine. I would understand that there's a small difference because you rounded a number, a value. But here, I know the computer, if you type 13,000, it's going to say that the answer is probably wrong. So I say, let's learn how to type this, everything the way that it's supposed to be. So I'm going to take a screenshot so that this can stay there. And you can see how it's supposed to be entered in the calculator. All this to get the exact answer, which would be this one right here. Okay. If we go back to the instructions, it was saying round your answers to the nearest cent. So if we go by that, the answer should really be $13,194 with 79 cents. If we're gonna round to cents. Okay. 79. So I'm telling you, I guess the best thing you can do is do the setup and learn how to enter it correctly on the calculator all at once so that you can give the calculator the exact answer. If not, it's going to say that it's wrong. So this is okay, but this is rounding and this is the exact answer. So I'm going to put here exact answer. And this is the answer after you're rounding, using rounding. So I would always say go by this. Okay. So in the next problems, what we're going to do is we're going to learn to do the setup, but then we're going to use the calculator so that we can practice how to use it. So that was part A. Part B says compounded quarterly. So compounded quarterly, we're still going to use the same formula. $10,000, it's the same investment, that's not changing. 1 plus the rate, it's going to be the same thing. Quarterly means 4, so 4 times the same times 7 years. Let's put everything here. 10,000, don't do step by step because then you're going to be chopping decimals like me and then you're going to get the wrong answer. Plus, it could be 0.04 or 0.04. I think I made a mistake right now within the force in that. Divided by 4 times 7. So the answer should be 13,212.91. 13,912.91. 212. And let me take a screenshot again. This thing is weird. I don't know, for some reason sometimes it doesn't let me put more screenshots after a certain part in the. Let's see if it can do the favor for me. Yeah. Okay, there it stays. That it wasn't going to stay. So okay. Probably not gonna be able to take a screenshot in the next one because I'm gonna have to keep on putting the picture down manually, taking it down, and it takes a while. So we're just gonna be like, I'm gonna show you with the calculator, but I'm not gonna be taking a screenshot anymore of the calculator. Anyway, you can see in the video what I'm doing. See, it says compounded monthly. Okay. So with the same information, A equals 10,000 times 1 plus 0.04. Monthly means divided by 12 raised to the 12 times 7. So we put again all this, 10,000 times 1 plus 0.04 divided by 12, close, close, raised to the 12 times 7. So 13,225.14. On the computer, I don't think you need to put a comma the way that I'm putting here by hand on the 13,000. If you put a comma, probably the computer is going to count it as wrong just because of that comma. Usually when we round larger numbers of several digits, every 3 digits we put a comma, or when you're dealing with money, but for the computer, don't put a comma because it might be counted wrong. Now D says compounded continuously. So what's the formula for compounded continuously? It's the other one. Remember, the key was continuously. So you're looking for the same thing, 10,000, it's the investment. Now this is a little different, times E raised to, what's the rate? 0.04 times the time. That's not changing, 7. So we put this in the calculator. 1, 2, 3, 10,000 times E. You may hit the times button or you may not. It's the same. If you just put the E right next to it, the calculator knows that it has to do a multiplication. 0.04 in the exponent times 7. Close the parenthesis. 13,231. Rounding to cents. 0.29. After the 9 there's an 8, so the 9 should go to the next digit, but it would be 10, so 30.30 cents. Okay. These problems are pretty simple. You just need to know your variables, okay, which are on the previous slide. So this is it. This is section 4.1. It's learning how to learning to know exponential functions, how to graph them, how to evaluate them, how to deal with the negative exponents, and how to do applications using the compound interest formula or the compounded continuously formula. Okay, so this is it.